Hi, Assalamualaikum warahmatullahi wabarakatuh. In this video, I'm going to give you a practical example related to the implementation of one-way Anova. And here what we have is conductivity data, where this is the effect on YouTube conductivity of 4 different types of coating for color picture tubes. And the data given here is based on a completely randomized experiment. And if you can see here, the coating types here are simply labeled as 1, 2, 3, and 4, and these are the 4 different groups based on coating types. And therefore data for this one here is based on group 1, and this is group 2, group 3, and group 4. Yeah, right. Using significance level of 5%, is there a difference in conductivity due to coating type? Now, when it comes to writing down the null hypothesis in general for one-way Anova, how we're going to write down the null hypothesis will be something similar to this one. Yeah. So in the null hypothesis, basically, the keyword here is related to no difference in the means of dependent variable no difference in the means of dependent variable when using different types of independent variable. So basically, this is the general idea of how you can write the null hypothesis, where the keywords here is no difference in the means, or no difference in the dependent variable due to using or to applying the independent variable on that. Okay, so therefore for the case given here, what we can do is we can write it down something along those lines, which means perhaps there is no significant difference. So we're just going to follow the idea given by this example here. We're just going to follow the construction of the sentence given there. So there is no significant difference in conductivity due to different coating type. Alright, so that is the null hypothesis, and you can see that the keyword here is no significant difference or no difference, which is in general what is the null hypothesis is all about for one-way Anova. Now, if you want to write down the alternative hypothesis, well, as I have said again and again, it is just a contradictory statement, and what we can do is we can write down there is at least one significant difference in conductivity in the means of the groups is also can. At least there is at least one significant difference in the means of different groups, or significant difference in conductivity due to different coating types. Okay, so there is at least one significant difference in conductivity due to, maybe if you want to be more specific here, what we can write down is we can write down different due to different groups of coating types. So here is different groups of coating types. Yeah, so perhaps that would be more clear to you. There is no significant difference in conductivity due to different groups of coating types, or there is at least one significant difference in conductivity due to different groups of coating types. Right, okay. Now the second step is to calculate the test statistic. And the test statistic is given by this one. F is equal to the mean squares between samples over the mean squares within sample. This is the test statistic as seen given here. Now, in order to obtain this test statistic, we need to be able to calculate what is SSB, the sum of squares for between samples, and SSW. So that is the step that we need to do. Now, in order to obtain SSB and SSW, these are the items that you need to figure out. You need to know what is T1 squared, T2 squared, and T3 squared, and so on. So in this case, we have up to T4 because we have 4 different groups. So what is T1? T1 is just the total of observation for group 1. So in this case, if you add up 143, 141, 150, and 146, this is the value equal to 580. So this is T1. If you add up this and this and this and this is 581. Okay, so the next one is for this row here. If you add up all the observations here, the answer is going to be 529. And if you go on and add up these 4 observations, that is going to be 517. And so this is the values of T1, T2, T3, and T4. Okay, now how about the next one here is what else you need the value of this one. So this is the sample group, the sample size in each group. So in this case, we have the same sample size for each group. So therefore, for this group here, N1 is equal to 4, N2 is also equal to 4, N3 is equal to 4, and N4 is equal to 4. So these are the sample sizes for each group. Alright, so what else that we need? Next, we need the sum of x. The sum of x is basically, you need the sum of x and you need to square it. So the sum of x can be obtained if you add up all these values here. So therefore, the sum of x is going to be equal to sum up all these values, or in other words, sum up all these values here. This is the sum of all the observations. This is equal to 580 plus 581 plus 529 plus 517, and that's equal to 2207. Okay, so now we've got all the components we need in order to obtain SSB, which is the sum of squares between. Okay, all right, let's just apply all the values into the formula given here. So what we have is we have 580, you square it over 4, plus 581 square it over 4, plus 529 square it over 4, plus 517 square it over 4. And then you're going to minus the sum of x is going to be squared. So we have 2207 square it, and then here, if you see the formula here, this is over n. N is the total sample size, which means it is going to be over 4 plus 4 plus 4 plus 4. This is going to be over 16. Okay, so the answer that you get here is going to be 844.6875. So that's the answer for the sum of squares between samples. Okay, so now let's look at the formula related to finding the sum of squares within sample. What we need here is this item here is the similar item which you have seen above. And then we just need an extra item, the new item we see, which is the sum of x squared. So in other words, this means you have to square each observation first, and then only you add them up. Okay. Alright, so in this case, what you need to do is you need to find sum of x squared, and this is basically you need to square this first. 143, you square it, plus 141, you square it. So you have to square all this single observation here until the very last observation, which is 129, and you square it. So square each observation given here until the very last one, and the results of that will be added later on. So based on this, what you will get is you will get the value of 305,509. So that's the value, and we're going to use this value and apply it into the formula for finding SSW. So what we have here is we're going to have 305,509 minus, we're going to minus the same item which you have already done here, and the value here is 305,272.75, and the answer that you will get is 236.25. Okay, so once you have managed to get the value of SSB and SSW, we are going to present the results here using this table. Okay, so I'm just going to write down what is the sum of squares for between. The sum of squares for between is 844.6875, and for sum of squares for within it is 236.25, and total sum of squares is going to be 1080.9375. Okay, right, next for degrees of freedom, this one is k minus 1. K is the number of groups, so 4 minus 1 is 3. So this one is obtained by having 4 minus 1, the number of groups, minus 1. And this one here, the degrees of freedom is going to be equal to 12. And how do you get this? This is based on n minus k. So n here is 16 minus 4 is 12. Next, you can take this value divided with the degrees of freedom, then you will get the mean square between, which is in this position. So the mean square between here is going to be 281.5625. And in a similar manner, you will take this sum of squares within, and then you divide that with the degrees of freedom. And so this is going to be equal to 19.6875. Alright, now for F statistic, so to get the value of F statistic, you're just going to consider this value and you divide that with this one here. So the F statistic is going to be equal to 14.3016. So that is the F statistic, which is normally calculated in the second step of hypothesis testing. Okay, so the third step is to find the critical value, and here we are talking about the F distribution, which is skewed to the right, and we see that the significance level used here is 5%, and this is the right tail test, therefore the critical region is just on the right side of the distribution, where the area is going to be equal to 0.05. So go to the F distribution table and search for alpha 0.05 on the top page of the F distribution table. Now the degrees of freedom here is according to this manner. Degrees of freedom, where the first position here is for numerator. So numerator is this one. This is numerator. So degrees of freedom is 3. Now degrees of freedom for denominator is 12. Oops, sorry. Degrees of freedom is 12 for denominator. And based on the column and the row given, you can find that the critical value, which is this one here. Oh, let me see if I have the table associated with this one here. Oh, I don't think I have this. No, I don't have the F distribution table here, but well, basically this is the distribution table for alpha 0.1. So instead of 0.1, you're going to look up for alpha 0.05, and so degrees of freedom for numerator is on this side, is on this one, and degrees of freedom for denominator is on this one, and you can just find the value based on the intersection of the value of numerator and denominator, for example. So that's how you're going to find the critical value, and I'm sure you can do it on your own. It is not that difficult to find the critical value from the F distribution table. Well, you will get that the critical value here is going to be equal to 3.49. So that's the critical value. Okay, so I'm just going to write down here for clarity. So critical value is 3.49, and therefore we are going to decide whether the null hypothesis should be rejected or not. And as you can see, this value here is 14.3016, which if I have this type of distribution table, therefore I know the position of 14 is going to be somewhere here, which is in the inside that critical region. So this is 0.3.49, so 14 must be somewhere very far ahead here. So 14 must be somewhere here. And because of that, okay, since the test statistic 14.3016 falls into the critical region, therefore H null can be rejected. Now, as a conclusion, we're going to say that there is enough evidence to support this alternative statement is true. So there is enough evidence to support this alternative statement. So we can say that there is enough evidence that at least one significant difference. So I'm just going to write down the conclusion. There's enough evidence to say that there is at least one significant difference. Basically, I'm just writing down the alternative hypothesis here. There's at least one significant difference in conductivity due to different coating types. Okay, all right, that's all for now. Thank you very much for watching, and I will see you in the next video with another example related to the implementation of one-way Anova.